The discovery that shattered reality. There was a time when humanity believed the universe was eternal, unchanging, and still. For centuries, the night sky looked calm and fixed, a silent dome of stars suspended in darkness. Philosophers imagined a static cosmos. Even when early astronomers mapped the heavens, they assumed the universe simply was, neither growing nor shrinking, neither beginning nor ending. But in the early 20th century, everything changed. And what we discovered would eventually reveal something far more shocking than expansion itself. The universe is not just expanding, it is accelerating. In 1929, at the Mount Wilson Observatory, astronomer Edwin Hubble made a discovery that shook science to its core. By studying distant galaxies through the powerful Hubble telescope, Hubble observed something extraordinary. The light from faraway galaxies was stretched, shifted toward the red end of the spectrum. This phenomenon, known as redshift, indicated that those galaxies were moving away from us. And not just a few of them. Nearly all of them. The implication was staggering. The universe was expanding. Imagine dots drawn on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. There is no central point on the surface, expansion happens everywhere at once. That is what our universe is doing. Galaxies are not flying through space away from a central explosion. Space itself is stretching, carrying galaxies with it. This discovery supported an earlier theoretical prediction made by Albert Einstein. Ironically, Einstein had originally modified his own equations of general relativity to prevent the universe from expanding. He introduced something called the cosmological constant, a mathematical term designed to hold the cosmos steady. When Hubble proved expansion was real, Einstein reportedly called the cosmological constant his greatest blunder. But the story was far from over. For decades, scientists believed that while the universe was expanding, gravity should be slowing that expansion down. After all, every galaxy pulls on every other galaxy. The mass of the universe should act like a cosmic brake, gradually reducing the expansion rate over billions of years. The big question became, will the universe expand forever, or will gravity eventually stop and reverse it in a catastrophic, big crunch? By the late 20th century, astronomers were determined to measure how quickly the expansion was slowing. Two independent research teams set out to answer this. They studied a special type of exploding star known as Type Ia supernovae, cosmic beacons so bright they can outshine entire galaxies. These stellar explosions act as standard candles, allowing scientists to measure vast cosmic distances with remarkable precision. The teams were the Supernova Cosmology Project and the High-Z Supernova Search Team. In 1998, both groups announced results that no one expected. The expansion of the universe was not slowing down. It was speeding up. The universe was racing apart. This was not a small correction. It was a fundamental shift in our understanding of reality. Gravity, the force that binds galaxies, stars, planets, and people together, was not winning on cosmic scales. Something else, something unknown, was overpowering gravity and driving galaxies apart faster and faster with every passing billion years. Scientists were stunned. To explain this acceleration, cosmologists revived Einstein's discarded cosmological constant. But this time, it wasn't a mathematical mistake. It appeared to represent something real, a mysterious energy embedded in the fabric of space itself. They called it dark energy. Dark energy does not emit light. It does not absorb light. It cannot be seen directly, yet it makes up about 68% of the entire universe. Ordinary matter, everything we see, from galaxies to atoms, accounts for less than 5%. Think about that. Everything humanity has ever observed is just a tiny fraction of what exists. Dark energy behaves unlike anything else known in physics. Instead of pulling, it pushes. Instead of clumping together, it spreads evenly throughout space. And as space expands, more space is created, which means more dark energy appears. The result, a runaway expansion, accelerating forever. But what is dark energy? One possibility is that it truly is Einstein's cosmological constant, a constant energy density of empty space. In quantum physics, even empty space is not truly empty. It seethes with virtual particles constantly appearing and disappearing. This quantum vacuum energy might generate a repulsive force. There's just one problem. When physicists try to calculate the vacuum energy predicted by quantum mechanics, the result is catastrophically wrong, off by a factor of 10 squared. It's the worst theoretical prediction in the history of science. That discrepancy is not small. It is not even astronomical. It is absurdly, unimaginably enormous. Which means something fundamental is missing from our understanding of reality. Another possibility is that dark energy is dynamic, a changing field permeating the universe, sometimes referred to as quintessence. Unlike a cosmological constant, quintessence could evolve over time. If true, the fate of the universe becomes uncertain. Acceleration might continue forever, or it might reverse. Some even speculate that our understanding of gravity itself is incomplete. Perhaps Einstein's general relativity breaks down over vast cosmic distances. Modified gravity theories attempt to explain acceleration without dark energy at all. To solve this mystery, scientists launched increasingly powerful instruments into space. The Hubble Space Telescope refined distance measurements. The James Webb Space Telescope began probing the earliest galaxies. The Planck spacecraft mapped the afterglow of the Big Bang with exquisite precision. And yet, instead of clarity, a new problem emerged. It is known as the Hubble tension. When scientists measure the expansion rate of the universe using nearby supernovae and Cepheid variable stars, they get one value for the Hubble constant. But when they calculate the expansion rate from the early universe using cosmic microwave background data, they get a different value. Both measurements are extremely precise. And they disagree. This is not a small disagreement that can be brushed aside. It is statistically significant and growing stronger as measurements improve. Either our observations are wrong, or our cosmological model is incomplete. Some researchers believe the Hubble tension could be the first real crack in the standard model of cosmology, the lambda CDM model that includes dark energy and dark matter. If that model fails, it means we are standing on the edge of a new revolution in physics. The universe is not just expanding. It is accelerating. It is behaving in ways that challenge our deepest theories. And the numbers refuse to reconcile. But perhaps the most unsettling implication lies in the future. If acceleration continues indefinitely, galaxies beyond our local group will eventually move away faster than light due to space expansion. Not because they are traveling through space at superluminal speeds, but because space itself is stretching. Over trillions of years, distant galaxies will fade from view. The observable universe will shrink. Future civilizations, if they exist, may see only their own galaxy cluster, surrounded by darkness. Cosmic isolation. The night sky will grow empty. The universe will become colder, darker, and more dilute, heading toward a scenario known as heat death, where stars burn out, matter decays, and entropy reaches maximum. But what if acceleration increases even more? Some theories predict a Big Rip, a future where dark energy grows so powerful that it tears apart galaxies, then stars, then planets, and eventually atoms themselves. Space would literally rip reality apart. Is that our destiny? Or is dark energy hiding something even stranger? In recent years, new observational data has hinted that dark energy may not be perfectly constant. Some early findings suggest it might be weakening, or evolving, over cosmic time. If confirmed, that would rewrite everything. The universe might not accelerate forever. It might slow, it might stabilize, or it might do something entirely unexpected. For now, we stand in a rare moment in cosmic history, a time when we can still see distant galaxies before they vanish beyond the horizon of expansion. A time when technology allows us to measure the deepest parameters of existence. And yet, the more precisely we measure, the stranger the universe becomes. The universe is racing apart, and we may finally be close to understanding why. But the answer could change physics forever. The crisis in cosmology. For decades, cosmology appeared settled. The equations worked. The observations matched. The model, known as lambda CDM, elegantly described a universe born in a hot Big Bang, shaped by invisible dark matter, and accelerated by dark energy represented by Einstein's cosmological constant. It was precise, predictive, beautiful, and then the numbers stopped agreeing. The crisis did not explode overnight. It grew quietly, almost invisibly, as measurement techniques improved. Astronomers were refining the Hubble constant, the number that tells us how fast the universe is expanding today. But the more precise the instruments became, the deeper the disagreement grew. On one side were measurements of the nearby universe. Using observations from the Hubble Space Telescope, astronomers like Adam Rees and his SH0ES team measured distances using Cepheid variable stars and Type Ia supernovae. Their conclusion was clear: the universe is expanding at about 73 kilometers per second per megaparsec. On the other side were measurements from the early universe. The European Space Agency's Planck spacecraft studied the cosmic microwave background, the faint afterglow of the Big Bang, with unprecedented precision. By analyzing subtle fluctuations in that ancient radiation, scientists could infer what the expansion rate should be today under the standard cosmological model. That number came out lower, about 67 kilometers per second per megaparsec. The difference might sound small. It is not. In cosmology, this discrepancy is enormous, far beyond experimental error. It is statistically significant at a level that suggests something fundamental is wrong. This is the Hubble tension. Two methods, two precise answers, one universe, and they do not match. At first, scientists suspected systematic errors. Perhaps Cepheid variables were miscalibrated. Maybe supernova brightness varied subtly. Could cosmic dust be skewing results? Teams rechecked their data, improved calibration methods, refined statistical models. The tension persisted. Then attention turned to the early universe calculations. Could the cosmic microwave background analysis be flawed? But the Planck data was extraordinarily detailed. Independent measurements from other observatories confirmed similar results. The conflict remained. This is not just a disagreement over a number. It is a challenge to the very structure of modern cosmology. If the early universe predicts one expansion rate, and the late universe measures another, then either our model of the universe is incomplete, or something dramatic happened between then and now. Some researchers proposed the existence of early dark energy, a brief phase shortly after the Big Bang when dark energy behaved differently, temporarily altering expansion. Others suggested unknown relativistic particles in the early cosmos, sometimes called dark radiation, might have influenced the outcome. There are even more radical possibilities. What if gravity behaves differently over cosmic distances than Einstein predicted? Einstein's general relativity has passed every test within our solar system and around black holes. But those are relatively small scales compared to the entire universe. Perhaps, on the largest scales imaginable, gravity subtly changes behavior. Modified gravity theories attempt to explain cosmic acceleration without dark energy at all. Some introduce extra dimensions, others alter the equations of spacetime itself. These ideas are mathematically complex, and none have yet provided definitive answers, but they demonstrate how seriously the crisis is being taken. The Hubble tension has forced physicists to question assumptions once considered unshakable. Meanwhile, new instruments are pushing the boundaries further. The James Webb Space Telescope is now peering deeper into cosmic history than ever before. By observing ancient galaxies formed shortly after the Big Bang, it is providing new insights into early structure formation. Some early observations suggest galaxies formed faster and earlier than expected, potentially complicating existing models even more. Every time we look deeper, the universe refuses to behave exactly as predicted. And yet, the acceleration remains undeniable. To understand how strange this is, consider what acceleration truly means. Imagine throwing a ball upward on Earth. Gravity slows it down. That is intuitive. Now imagine throwing that ball upward, and instead of slowing, it accelerates away faster and faster. That is what galaxies are doing relative to each other. Gravity should slow expansion. Instead, something is overpowering it. Dark energy appears to have negative pressure, a property that causes space itself to expand faster as it grows. In Einstein's equations, pressure contributes to gravity, and negative pressure creates repulsive gravity. The more space there is, the more dark energy exists. The more dark energy exists, the faster space expands. It is a feedback loop, and it is accelerating. If this continues unchanged, the far future becomes bleak and lonely. In roughly 100 billion years, most galaxies outside our local group will move beyond our cosmic horizon, permanently unreachable and invisible. Future astronomers would have no evidence of the Big Bang. They would see only a static island universe surrounded by darkness. Cosmic history would be erased from view. But what if dark energy evolves? Some observational hints, still tentative, suggest that dark energy might not be perfectly constant. If it weakens over time, acceleration could slow. If it strengthens, the Big Rip scenario becomes possible. In a Big Rip universe, acceleration increases without limit. First, galaxy clusters would separate. Then individual galaxies would be torn apart. Eventually, gravitationally bound systems like solar systems would dissolve. Finally, atoms themselves would be ripped apart as spacetime expansion overwhelms fundamental forces. The timeline for such an event, if it were to happen, would be tens of billions of years away. But the mere possibility reveals how little we truly understand the dominant energy component of reality. The deeper truth may be even stranger. Some physicists speculate that dark energy is not energy at all, but a property emerging from quantum entanglement on cosmological scales. Others suggest our universe may be one of many in a vast multiverse, where dark energy is simply the vacuum state of our particular region. In certain interpretations of string theory, the cosmological constant arises naturally from the landscape of possible vacuum states. But that landscape contains an enormous number of possibilities, raising philosophical questions about why our universe has the value it does. Too large, and galaxies never form. Too small, and the universe collapses. Our cosmos appears finely balanced, expanding fast enough to accelerate, but slow enough to allow structure and life. Is that coincidence, or something deeper? As measurements improve, one thing becomes increasingly clear: we are living at a pivotal moment in scientific history. The tension in the data may represent the first real crack in our cosmological framework in decades. Just as Hubble's discovery shattered the idea of a static universe, the Hubble tension may shatter our understanding of cosmic acceleration. The universe is racing apart. We have measured it, we have confirmed it, but we do not yet fully understand why. And that uncertainty is not a weakness of science, it is its greatest strength. Because when the universe refuses to match our equations, it forces us to discover something new. Something deeper, something that could redefine space, time, gravity, and reality itself. We stand on the edge of a possible revolution, one that may reveal whether dark energy is a constant, a field, a flaw in gravity, or a sign of something far more extraordinary. The cosmos is expanding faster every second. The numbers do not agree. The tension grows, and somewhere within that tension lies the answer.